Hello everyone, this is Ravi Thapa. Today I am going to present on a next generation object-oriented environment for real-time database application development. This paper is taken from 12th IEEE International Conference on Trust, Security and Privacy in Computing and Communications, published in 2013. In this paper, authors have given an example of such applications which interacts with dynamic environment and that are typically supported by real-time database system. For example, agile manufacturing, traffic control, and target tracking, and which has a sensor and which senses the real-time environment data and derive accordingly. So these type of application often involve real-time world entities, and they have a complex relationship among them. So I will explain a little bit about the real-time data and how they are derived, and after that I will explain a little bit how the object database is introduced and introduce after that. So so real-time database manipulates real-time data and executes real-time transactions. So real-time data are divided into two types. Like I said, since it uses sensor, so one is sensor data and one is derived data. Sensor data are periodically collected from the physical environment through sensors, and the derived data are the computed data from sensor data. So when a sensor data item changes, all derived data items that are based on it need to be recomputed, and accordingly there should be transactions. So real-time transactions are also classified into two categories. One is update transaction and other is user transactions. So update transactions are executed periodically to update sensor data or sporadically to update derived data. So what happens is user transaction actually, which represents user request, and the update transactions are executed periodically to update sensor data or sporadically to update derived data. And the real-time database must maintain, in this course of transactions and the applications, a real-time database must maintain the logically consistency as well as the temporal consistency of the data, because since we are dealing with real-time applications, it should look like that this is real. Not 100%, but it should look like this is real. So logical consistency is supported by most conventional databases. Actually, data temporal consistency is defined as how well the data maintained by an real-time database. And there are two forms of real-time data consistency constraints. One is absolute and relative. The absolute temporal consistency requires that a data item's age must be within a certain interval of the current time. The relative temporal consistency represents the required correlation among data used together. So a real-time database requires enforcement of the temporal consistency of transactions in addition to their logical consistency. So transaction logical consistency constrains the value of result produced by transaction, while transaction temporal consistency requires that transactions be treated as real-time tasks with timing constraints. So object database for real-time application development on the top of DB40 database management system. So this comes after the limitations of the existing real-time database system, and query language, real-time native query language, a powerful new high-level RT object-oriented programming language which is tightly coupled with query capabilities. This language will come after when we see in the system overview how it works with the real-time applications. And also we'll discuss on the design goal of ODEA and its fundamental mechanism in later part. So what makes this object database application introduced? We have already existing real-time databases that are not open to public, because there are a lot of real-time databases system, but those are based on simulations, and there are some limitations that in comparing and verifying existing core techniques for real-time databases performance management. And there are commercial real-time database products, example Eagle Speed, Plyhedra, TimeStain, and ExtremeDB, but most of them have very limited real-time features. So most of them do not apply the latest real-time database technology. So what authors have concluded that they need more object-oriented database applications system, so that they can build application on that. So so the researchers on real-time database have been actually initiated for more than 2 decades, producing key results. And although these products may be considered a true database system from the viewpoint of many researchers in the RT database community, since most of them do not apply the latest RT database technology, they represent a significant step for the success of real-time database system. So they came up with the object-oriented design. So real-time objects are the real-time database entities. They represent dynamic entities of time-critical systems in the real world, and they also have real-time attributes, represent the real-time data stored in the real-time database and manipulated by real-time methods. All these enhancements are strongly motivated by real-time data management and the applications. So in this system, they have also the feedback control scheduling architecture, which monitors the timing constraints. So the execution of transaction within their deadlines with fresh data to reflect the real world status. So it has to execute its work within certain time. So the transactions timeliness and data freshness requirements may compete for system resources, and the ODEA achieves the desired quality of service using feedback control scheduling theory. So another query language is a real-time query language extended to our programming languages, and it has a full computational power of programming languages, and it expresses database queries with Java syntax completely without the use of strings by providing full compliance with the Java language specification. So real-time native query language eliminate the need to learn other database APIs besides Java. So this is very powerful language. So looking at the system overview, here in figure 1 you can see that this is overall ODEA system. This ODEA supports the object-oriented data model, and it is organized as a multi-threaded server. The ODEA design is composed of native ODEA clients, legacy clients ported to ODEA, and interface to legacy system outside of ODEA. It is assumed that ODEA native clients are physically disparate from the ODEA server, so they pass messages to communicate with the ODEA server. So you can see here in the figure that how this RT and QL program is located here, and it will interact, and the client will use this RT and QL program, and it interacts with the ODEA database server, and the finally to the relational database, object database, and XML database through the ODA wrapper here. A native ODA client can be programmed, written in RT and QL that we saw in that diagram, and can run in ODEA, as well as a legacy program connected by a standard middleware, for example a JDBC gateway, web service gateway. And the ODEA permits porting of the database into the ODA system by a combination of wrappers and changes to the underlying software of these databases. And the system will access this database using RT and QL. From here, they will use this RT and QL program. Using that program, they will access the databases. Looking into the architecture, we have this diagram. This is the whole architecture, how these clients interacts with the server, and there are different components here. And in the client, there are different. They are using integrated development environment with the source program in RT and QL, and there is a ledger and parser type checker here. So these are all the architecture where the installation can work as a client as well as a server. Many clients can be connected to a server, and a client can be connected to many servers. So user can submit transactions which are RT and QL programs from client side, as we saw in the overview diagram also, and the architecture diagram also. A source code of an RT and QL program is created within ODEA IDE development environment, which includes an editor, a debugger, storage of source and compiled programs, etc. Lecture and parser module takes a source code as input and makes a syntactic analysis. Going to the next slides, the compiler to bytecode module takes the checked source program and produces a bytecode that is ready to execute. The data model includes timestamp data, data with validity intervals, and data with maximum data error interval. And the authors have used a feedback control scheduling architecture to guarantee the target deadline miss ratio of transactions. ODEA object model. In the ODEA architecture, the user sees the database as a set of real-time objects and a set of real-time transactions. So what real-time objects includes? An ODEA real-time object is a tuple, and it has certain, you can see here, there is N, A, M, C, L, C, B. These are in which N is a unique name, A is a set of RT attributes, and M is a set of RT methods, C is a set of constraints, L is a local controller, and B is a set of behaviors. So these are the objects in ODEA architecture. And the attributes, the real-time attributes, the second component of a real-time object, the A is a set of attributes where each attribute is characterized by N, V, T, V, D, M, D, U, O, and V. So if you look into the architecture, or later it will come in the diagram, and you will be clear on that on the diagram. So real-time methods. So the third component of real-time object, M is a set of real-time methods. Each method is characterized by these components here. So this is an example of aircraft real-time object. So as we mentioned earlier, there are different attributes for the real-time attributes. For example, here you can see in aircraft class there is an attribute here. So identifier, destination, altitude, and so here N is the aircraft. For example, here if you go back here, okay, if you see here is real-time objects, as in real-time objects in a tuple, there's N, A, M, C. Likewise, you can see here N is aircraft, A is an identifier, likewise. So this is the whole aircraft RT object diagram. So ODA object model, there are some constraints. The fourth component of a RT object, C, is a set of constraints. Constraints permit the specification of a correct object state. Our constraint specification is based on the model introduced, where a constraint is characterized by these attributes here. So in conclusions, that what we have concluded, that it was realized that Due to rapidly growing technology in sensor and wireless technology, real-time database application is very